My name is Alejandro Gonzalez. I am the captain of VantTec, and I'm also in charge of the guidance, navigation, and control system of our USB, the VantTec S3.
Hi, my name is Pedro Sanchez. I am the co-captain of VantTec. I was in charge of the systems engineering as well as the software architecture.
Hi, my name is Elena Collado and I'm head of perception at VantTec. I work specifically on optical detection, collision avoidance, and sensor fusion.
Hi, my name is Roberto Mendivil and I am the head of USB software. I work on the software architecture, challenges implementation, and guidance.
Hi there, my name is Sebastián Martinez and I am part of the RoboBoat team. My job consists in developing the software architecture and in helping with communication.
Hi, my name is Mildred Gil and I'm the head of the UAV software. My team and I were in charge to develop the Android app for the drones control.
My name is Alonso, head of embedded systems. My team and I were tasked with developing an hydrophone array for the acoustic docking challenge.
Hi, my name is Samuel Ortiz and I am the head of mechanics, and my work is focused in the USB design.
Hello, my name is Ángel Ceballos. I'm the head of electronics and my role is to design and implement the control board for the USB.
Hi, my name is Edison and I work with the RoboBoat team. My job is developing a graphic user interface for the VantTec S3.
Hello, my name is Jorge Carlos Medina and I work in embedded systems.
Hi, my name is Ernesto Monroy and I collaborate in embedded systems department.
Hello, my name is José Miguel Carrillo. I'm part of the UAV team and I worked on the autonomous control of the drone.
Hi, my name is Andrés Sanchez. I work in the development of hardware and systems.
Hi, my name is Francisco Rojas. I am team member of the hardware.
Hello, my name is David Barragán and I do research in the field of artificial intelligence.
Hi, my name is Nadia Garcia and I'm the head of media development.
We are VantTec, a group of students from Tec de Monterrey focused in the research and development of autonomous vehicles. We want to inspire generations of young students to get involved into research and development in their areas of interest from the start of their careers, and help them to learn about national and international opportunities for both academic and professional paths.
This is our video submission for RoboBoat 2020.
Since 2019, the road operating system has been the backbone of our software architecture.
This year, the whole system was redefined, and it now integrates different ROS custom packages as shown next.
Some of the problems with last year's model included a very inefficient communications architecture, as well as a very unreadable code. This year, for RoboBoat 2020, we present a full duplex communications protocol between the boat and the ground station, as well as new coding standards that improve the readability of our code, allowing for a more efficient development process.
Our participation during RoboBoat 2019 implemented a class of backstepping controllers similar to a PD controller to achieve heading control. It was also adapted for GPS navigation, though it was not the most efficient or robust control strategy. And we also faced an issue with the lack of performance against environmental disturbances. This year, research was performed to design and implement a path-following controller based on adaptive sliding mode control and a time-varying look at distance, line-of-sight guidance law. A robust performance while navigating between waypoints is expected, which could improve the motion of the USB during each course run. A methodology to increase robustness in challenges is also proposed, improving our previous year work by replacing a type of visual surveying strategy and adding coordinate transformations to increase robustness into the guidance of the vehicle.
Same as in RoboBoat 2019, the perception system is made up of two sensors, the set stereo camera and the Velodyne VLP16 puck. The RGB image from the set stereo camera is used mainly to detect buoys and markers using the custom-trained convolutional neural network YOLO-TinyE3. The stereo point cloud is used separately to calculate the distance to the detected buoy. The lighted point cloud is used for general obstacle detection, benefiting from the 360-degree field of view. Avoidance methodology was developed for the solution of the obstacle field challenge. This static collision avoidance algorithm is based on the improved velocity obstacle method, meaning it does not require global environmental mapping, relying only in reactive avoidance and making it suitable for low computer and power budgets while running in real time.
The hydrophone array was designed to accomplish the goal of detecting an acoustic finger position relative to the USB position. This array will be connected to a custom-made amplification circuit, which has some improvements over last year's design. It has a higher input impedance and a low filter phase. For the high filter noise, a digital filter was proposed. 3 equal circuits are expected for each of the 3 hydrophones.
For signal processing, a microcontroller unit is used. Signals are read from the EDC integrated in the unit and then processed to obtain the angle of the finger with respect to the USB position. Then, it is fed to the control system via I2C communication, where it is used to set a waypoint for the boat to perform an automated move. FreeRTOS, a real-time operating system, was implemented to be able to add other applications to the microcontroller unit in the future, given the wide range of capabilities it has, and allowing us better research management given the hard and soft time constraints.
FreeRTOS, real-time operating system, was implemented to be able to add other applications to the MCU in the future, given the wide range of capabilities it has, allowing a better MCU resource management given the hard and soft time constraints.
Another that was developed for the USB and the UAV communication. It offers a manual mode controller with essential actions to pilot the UAV, as well as a recording and shooting mode for the camera with the purpose of having a visualization of the navigation path. The user is able to launch their waypoints in a Google Maps environment for a specific route and create a geofence.
The use of DJI SDK virtual sticks allows for an autonomous control of the drone, emulating what a real controller would do, and their values can be set via code or by the camera view.
To improve the USB state visualization and increase the operating practicality, a graphic user interface was developed using the JavaScript library React.js and a ROS package for JavaScript, making the establishing of communication with a web browser possible, as well as the implementation of a monitoring system.
There are 3 main characteristics in our proposal strategy for this year's competition: research-based solutions, practicality, and funding management.
Since our goal was to participate in both RoboBoat and RoboSub 2020, we decided to go with the same vehicle platform we have been using for our past 2 RoboBoat participations. This time, however, we decided to develop 3D printed mountings and casings for our electronics, as well as new printed circuit boards, which allowed for a better arrangement inside the vehicle and more efficiency in space.
Taking into account the team's experience, particularly after reaching the finals in 2018 edition, publishing a paper about some of the technologies developed, the overall strategy focuses on algorithms to solve all the competition challenges.
Achieving the mandatory navigation challenge, which was successfully accomplished in RoboBoat 2019, anticipated have higher importance than the other challenges, as the first one is used basically as a basis for the next ones, and this year's strategy relies on robustness and research-based justification that the system will be capable of succeeding at higher rates.
RoboBoat 2019 presented a big step on the obstacle field task performance. However, the collision avoidance algorithm implemented was not robust, and was designed and implemented only a week before the competition due to delayed hardware delivery. Following the problem of hitting buoys in the previous edition, an objective this year was a much more robust approach to avoid any obstacle during the challenge and overall navigation.
Acoustic docking and object delivery task implies subjects the team has not tackled before. 2 sub-teams were created to focus on both challenges, making this the first year the team will have arrived with a working hydrophone-based solution. The strategy in this challenge is to accomplish an acoustic and laser-based solution, combining independent sensor data to improve the docking maneuver.
The second sub-team topic, object delivery, implies cooperating with an unmanned aerial vehicle, which is something the group has achieved in previous years since the delivering objects only with the UAV, since changes to the USB were avoided.
The strategy for obstacle channel initially relied on learning from the known challenges from previous competitions, and used that learning to think of solutions for this new task.
This decision led to the work on the obstacle challenge after the rest of the challenges were achieved. However, with time, the strategy became to use the same principles learned from the other challenges and adapt them into the obstacle challenge environment.
Therefore, the strategy proposes that by working with a known platform, improving and adding robustness to previous approaches, designating sub-teams for specific technical challenges, and spending considerable time in simulation, achieving a better performance than previous years is feasible at the 2020 RoboBoat edition. Initially, to reduce time spent debugging software at field experiments, a simulation environment was proposed.
The necessity to have a simulator increased as the pandemic started and became a great solution for continuing working on the USB autonomy.
Running in a ROS environment parallel to the platform software architecture with RV's visualization, it was built on the mathematical model and simulation of the INS feedback data and stereo camera and LiDAR and hydrophone detection outputs.
This simulation environment allowed for the possibility of recreating the RoboBoat challenges, obstacle detection, and the algorithm testing.
As the COVID-19 pandemic grew, the algorithms could only be tested in simulation. Simulation results demonstrate the capabilities of the proposed task solutions. Results show the course approach is feasible, as all of the course tasks involving only the USB were successfully accomplished.
More than a boat, a drone, and research, we are people from all around Mexico and Latin America with the same goal in mind: to make an impact on society, no matter what